Hey guys, it's Jimmy here. It's been a long time since I uploaded any videos because I'm currently grade 11 and I'm kind of busy with all the coursework within school and also other competitions and tests. And finally, it's now Christmas break, so Merry Christmas to all of you guys, and also Happy New Year in advance. So in this video, in my previous videos, I've covered the fundamental ideas of analytical mechanics. In this video, in my further videos, I'll talk about some of the exercises that I think is about mechanics and is kind of good and will be kind of beneficial. So today, in this video, I'm gonna talk about one of the exercises from the book Exercises for Feynman's Lecture on Physics. It's actually a good set of exercises because I think all the exercises are kind of creative and straight to the point. So I think those who are enthusiastic about mechanics and or even the physics can try it because it covers not only mechanics but also electromagnetics and some basic quantum mechanics, also thermodynamics, probability, probability theory, and a lot of content from physics. Okay, without further ado, let's get into this problem. So let's first read it. An L-shaped uniform rigid bar of mass m with legs each of length L, hangs from its upper end A, pivoted to swing freely in its own plane, as shown in the figure. So here's a pivot, and the first question. Hold on a second. Okay, the first question is at what angle theta 0 with vertical does it hang when at rest? So actually, first, this problem seems quite easy. You see, there's no numeric values in the text. However, it's for the second question, it's kind of hard to solve. We'll later get down to why. Okay, good. Okay, for the first question, we're calculating the angle theta 0 when hand at rest. So first you notice that it's an L-shaped rigid bar. So it's kind of hard to it's kind of irregular because it's bent into an L shape. So it will be much simpler if you think it as two single separate rods, two rods. So here's the first rod and here's the second rod. So their center of mass is here and here. So when at rest, I think all of it's common sense that one of the center of mass will be on the left side of the pivot, and the second center of mass will be on the other side of the pivot, so that the two torques inducted by the gravity will cancel out each other. Because if they are both on the same side, like if they're all on the same side like this, here's the center of mass and here's the center of mass, a problem will be caused because the two gravity has the same direction of torque. So it will cause the L-shaped rigid body to rotate counterclockwise. Okay, now we have determined how this rigid body should look like when it hang at rest. Then we're starting to calculate the angle theta 0. So we're using the we're using the balance of the two torques caused by these two gravity here. So the first one is the torque caused by this gravity on the left side. So torque M equals F times R. Oh, it's in vector form. I put it in vector form. So actually it's R cross product times F here. So but now we're not considering about the vectors here because we're just we obviously know that these two are on opposite directions, and that's why they cancel each other. So it can balance when at rest. Okay, so first we're calculating the R on the left side. So the R is here, so it's according to simple geometry, its value is 1/2 times L sine theta 0 over here. Okay, this is the first term. Okay, the right side of the equation should be 1/2 times mg, which is this force here. But however, the R is quite different. The R is here. Okay, so we can see the geometry is like this. So these two triangles are congruent, obviously. It's simple geometry. So this angle should be theta 0 as well. Okay, so then we can easily calculate the distance here. The distance here should be 1 over 2 times L times cosine theta 0 minus L sine theta 0. So after simplification, we will find that 3 sine theta 0 equals cosine theta 0. So then tangent theta 0 equals sine theta 0 over cosine theta 0, and it's 1 over 3. So theta 0 equals arctangent 1 over 3. So, okay, the first question is kind of simple. Okay, then we move on to the second one, which I think is kind of challenging. If an impulse J is applied at the elbow in the direction below, so here is the elbow. Okay, so it's an impulse is applied here. It produces an undamped small oscillations. So we're finding the expression for theta after there was the impulse is applied. So it was applied at t equals 0. So the time is 0. So it was applied at the start. Okay. Then we're starting to analyze the problem. So first, you can see it's about oscillations, and the whole problem is about rigid body. So first, we're obviously calculating the moment of inertia. So the rigid body. Okay, let me clear this. The rigid body is hand at this pivot, and it's rotating clock. So an impulse is applied at here. So obviously, it will rotate counterclockwise, like this. So how to calculate the moment of inertia about this point? Okay, so now I introduce parallel axis theorem. So it states as follows. I equals over here. I equals ICM plus M times D squared. So it states that the moment of inertia about an axis, which is like, for example, in this diagram, it's z prime. Okay, it equals the moment of inertia about the center of mass. Let's see, this is a rigid body over here. This is a rigid body. So it has center of mass on this point, and the axis over the center of mass for this rigid body is the z-axis. So the moment of inertia about this axis plus the mass of the rigid body times their distance apart squared is equal to the whole moment of inertia about the z prime axis, which is the one we're looking for. The derivation is kind of simple. So according to the definition of moment of inertia is I equals the integral of r squared times dm. Okay, then we have this formula over here. So we put it in Cartesian coordinates since the rigid body is in a two-dimensional plane. Okay, so it's equals to the integral over x squared plus y squared times dm. Okay, so this is the moment of inertia about the center of mass, which is the z-axis. Okay, now we move on to the z prime axis, which is because we're supposing a center of mass as the origin. So for each point, so this is the x-axis and this is the y-axis. So the center of mass cm is the origin. So we consider every single point on this rigid body, and we put it in an integral to sum it. Okay, so for the moment of inertia we're calculating, which is about the z prime axis, we change the expression under the integral to x minus d squared. So it's in coordinates. So I guess it's kind of simple to understand. Okay, so then we break it apart and we'll get this. Okay, so here's three terms over here. So this term obviously is equals to this term, and it is ICM. This term is equals to 0. Here's why. So the coordinates x of the center of mass is equal to this. is the sum of the sum of each for each point on the rigid body. It's sum of m times its coordinates over its whole mass. So we're considering the origin. We're considering the center of mass as the origin. So its coordinates ought to be 0. So here we turn it into an integral since it's kind of similar, and actually it is equivalent here. So this expression equals this expression, so it equals 0 given this. Okay, so this term is 0, and this term should be, because we're integrating all the mass, so this should be m times d squared. So, and here's the here's the final form of this theorem. Okay, so the parallel axis theorem I just talked about will help us calculate the moment of inertia of this L-shaped rigid body rotating about this pivot, this axis over pivot A. So actually we're applying the parallel axis theorem twice. So here's why. First, we need to okay, so the reason why we're using this theorem is because we cannot effectively calculate the moment of inertia directly, because the definition is given us as the integral of r squared times dm. However, this rigid body is kind of irregular, because the mass points over consider every single point on the rigid body. The distance, the expression for distance to the point A will differ. So that's why it's kind of difficult to calculate the integral directly. So we're considering first calculating the moment of inertia over the center of mass of these two rods. So the center of mass is obviously the midpoint of two midpoints of the rods. So it's over here. Here's the CM. Okay, how to calculate the after calculating the moment of inertia around the CM of the rigid body, we then add ICM plus we then add m times d squared. So this is the distance of d from this CM to the point A. Okay, so first the question remains, how do we calculate the moment of inertia around the point CM? Okay, we now here's the first time we used the parallel axis theorem. The second time we're using the parallel axis theorem is calculating the ICM. We're calculating the 2 times ICM rod. So we're calculating the moment of inertia of the two single rods over this CM rod, as I put it here, and then we add these two together. We add the m of the rod, the mass of the rod, and times this distance. Let it be actually labeled here. So this is D2, this is D2, and this is D1. So actually here's D2 and this is D1, and now we add 1/2 times m, because this is mass for a single rod, and the two coefficient 2, because we have two rods here, is times at the front. Here's a bracket, and 1/2 m times d1 squared. Okay, so this is the ICM, and after calculating the ICM, we plus the total mass times d2 squared. Okay. So this is step by step how we calculate the moment of inertia around the pivot A. Okay, so actually for the ICM rod, this term here, it can be simply derived from the definition, because you see this is a rod and has CM here, and has known 1/2 m times an L. Okay, so the definition of the moment of inertia is integral over r squared times dm. So okay, it equals 2. This is 0. This is 1/2 L. This is 1/2. Okay, so it's basically 2 times integral of 0 to O and R squared. So dm is equal to dr over L times m. Okay, we substitute this in times, oh sorry, m over L. So it will result in 2m over L. Oops. What is this? It is 24 L cubed, and this will cancel out. This will cancel out, and it will remain. Okay, so this is how we just use the definition for the moment of inertia, and we can directly derive the expression for the ICM broad term over here. Okay, so I did the calculations when preparing this for this video. So the value is the total value after substituting all these values in it, it will be 5 over 6 times the big M times L squared. Okay, now we have successfully derived the moment of inertia around the point A pivot. Okay, so then we're using the equation for the rotation of rigid body. So similar to the Newton's second law for a mass point. So for a mass point, we know that F equals ma. So for the rotating rigid body, we can, like, it's an analogy. So F is similar to m. So, and the mass equals is kind of similar to moment of inertia, denoted by I here. So A, the acceleration term here, is actually equal to the coordinate x, the second derivative of the coordinate x. So you can check on my previous videos about analytical mechanics, and you'll find this kind of denotation kind of easy to understand. So we're dealing with rotations here. So we're replacing the second derivative of x with the second derivative of theta, which is angular acceleration. It's kind of similar. It's an analogy. So with this equation on the left side, we can solve almost all of the problems about mass points. With this formula on the right side, we can handle most of the problems with rigid bodies. Okay. Now we move on. We now already know the term I. Okay, so I times the second derivative of theta is equal to m, big M. This m, okay, sorry, this m is not mass. Sorry, I forgot to mention. So it is a torque. So this torque contributes to the angular acceleration of the rigid body. So this is how we should understand how this what is the torque and its contribution to the whole motion. Okay, so I drew a diagram here. So after time delta t, the L-shaped rigid body will move. We'll have angular displacement of delta theta over here. So let's consider a random point on the rigid body, like point P over here. So here's 2 points. So this is point P and this is point P prime. So the P prime is where P should be after time delta t, and so it will receive a force, a gravity force of like dm like times g, and this is also dm times g. Dm is like a tiny little amount of mass. So it's the gravity that causes the point to have angular displacement, and the displacement is this arc. So this arc is this distance times delta theta, like L times delta theta. So times dm times g is equal to the rotational inertia of this single point P about the axis A, and times the angular velocity. Okay, so this is how a single point on the rigid body should look like. However, we are now considering the whole rigid body, we're considering the whole rigid body, so we should integrate both sides. So the integral of dm should be the integral on the left side should be the L should be the center of mass to the point A. So this this should be equivalent to this d2 over here. So should be d2 times d theta times the integral of dm is obviously m times mg over here. Okay, so for the right side, it should be the moment of inertia about the whole system about the point H, which is just what we calculated over here is 5/2 times ml squared times the second derivative of theta. So this is how this equation of motion should look like. Okay, so we write the integral of d theta as just theta, plain theta t. Okay, d2. Okay, I forgot to mention here. So the value of d2 is equal to, and it's just simple geometry. Look at the diagram here. It's the purple diagram. This is the L shape, and this length is d1. This we just calculated, and this length is d2. This purple line here is d2. So this is kind of simple to calculate because they have the equal side lengths, and also this is right angled, so everything will be just about either times the whole coefficient of the 2 squared, and it's simple geometry. So we got d2 equal to this value over here. Okay, back to this equation. Okay, we forsake this integral because after integrating over d theta, we'll just get an angular displacement of theta minus theta 0. It's just angular displacement. Sorry, displacement, and the right side remains the same. 5/2. Okay, and this is exactly what we get over here. This equation. Okay, so now we have successfully obtained a second order differential equation about theta. Okay, it's a second order differential equation. Okay, then how should we solve it? The standard way of solving a second order differential equation is to introduce a thing called trial solution over here. This is standard way of doing it. Typically, the solution for the equation will contain the sinusoidal functions, which includes both sometimes both cosine and sine functions. The reason why is that you'll notice that the second derivative of a function cosine theta is minus sine theta prime equal to, or sine theta prime is equal to minus cosine theta prime equals to minus sine theta. So both of these will have something to do with the original function. They'll have there's just an inverted sign. So these will typically in most of the times the second order differential equation will contain sinusoidal functions. Sometimes we convert it into exponential functions with imaginary numbers, but that's another way of solving it. That's another similar way of solving it, because you can use the Euler's formula to transform it into sine functions, cosine functions as well. Okay, after we utilize the trial solution, we substitute the boundary conditions in it. That's the different derivatives when the function theta about the parameter t. When the t is equal to 0, we get a set of different equations, and we'll be able to calculate the specific values for a and for the value over here a and b. But before that, we need to realize something, because if we just do that, we'll miss. We'll be unable to calculate the value for this omega right here. This is a very important factor, because this is the angular frequency or frequency of the oscillation, because we're dealing with oscillations here. So the solution for this function the solution for the this equation, which governs the motion of the rigid body, will be very important, and it will contain the sinusoidal functions inside, and contain the omega t. Wait, let me put this on brackets so you guys can see it. So this is called angular frequency of the oscillation. We're missing a equation here. The equation we're missing is the general form of SHM equation, which takes the form of this. So whatever is the coefficient of the of theta is omega squared. Okay, so with this function, we transform it to this form. Okay, so theta, this term before theta is actually the square angular frequency squared. Okay, then we'll be able to calculate the angular frequency after square rooting this term. So this is just simplification to make it look more adorable. Okay, so we now get the angular frequency, and now we substitute back the boundary conditions. So we actually, here's another detail here. We're given here the impulse. What is an impulse? Impulse j equals to the integral of f times dt. Okay, so we now have also another equation called m equals to I times the second derivative of theta. Okay, what will happen if we integral m over time? Here's what will happen, because torque equals to F times L, force times distance. That's common sense. Okay, so after we break apart into F and L, we discover that F and dt will come together and become J itself, and L will remain the same over here. It will become JL, and then we break M apart using this equation here. We'll be able to get I theta, the second derivative of theta times dt. Okay, then I will remain the same because it doesn't contain any parameters about time. It would just be and it will be the first derivative of theta, which is of course the frequency or the angular velocity of the motion. So in this case, actually, the theta is decreasing because you see here's theta 0, and here's another theta. So theta is an angle that is smaller than theta 0. So theta minus theta 0 will be negative. So the theta is decreasing. So the derivative of theta will be negative. So, but actually the impulse times the distance L will be always positive. So we invert the sign, we turn the right hand side to be negative. So both of the right hand side will be positive values. Okay. And this is one of the most important boundary conditions, because we are utilizing the condition J given in the context. This is very important because J is kind of awkward. Most of the people don't know how to utilize this condition, but it's actually very important for our problem solving process. Okay, so this is one of the boundary conditions when the time is 0, because you see when J was applied at t equals 0. When t equals 0, the value for the angle is theta 0. And here's the other boundary condition. Theta dot 0 equals theta dot 0 equals that is what we derived over here. You see, here's JL and here's I times theta dot. Okay. So with this, we can now calculate everything, because we now have already know what the solution should look like. We have the trial solution here, and we have already calculated the angular frequency or the angular velocity of the rigid body. It's actually the same. Okay. Then we're substituting everything inside, and from this boundary condition, we substitute when time is equals to 0, and the value cosine 0 equals 1 and sine 0 equals 0. So we'll get that the coefficient a is equal to 0. So we now know the solution takes the form. The solution does not contain any cosine function inside. It would just be sine functions. And we take the first derivative of the function, and it will be omega times b times cosine omega t, and we substitute the second boundary conditions. So this is BC1, this is BC2, and we'll get, because we already know the value for omega over here. So we just want to know the value for b. So after substituting this inside, we'll get the value for b, and the solution will take the form as follows. So this is the final answer for this problem. It's very complicated from the answer, but you see, so every step makes sense, and I guess this is the magic fit of physics, because you see, a simple problem like this will take so much steps and time, and eventually will have such complex solution, and it's very intricate, and it cannot have mistakes. So one mistake can result in your false predictions about the motion of the rigid body. So I guess that's the magic of physics. And so this is a problem I want to share with you guys. I think it's kind of beneficial for those studying physics, and some of the also includes some mathematical skills, like the geometry. In this problem is kind of simple, but the standard way of solving a second order differential equation is kind of helpful to your maybe very kind of helpful for your future studies. Okay, so this is all the content I'm introducing to you guys. So hope you have a great day and enjoy the video. Thank you.